I just would like just to express how happy I am to be able to work with these guys that just talked before. It's really great being part of this community of wine science experts. And the fact that I am also very fortunate to have a very small but very good team composed of 4 people only, but very good team. So the only problem that I have in this world, if I can say so, it's more about my boss making all these stupid jokes every time that he does an introduction. I think there's nothing that I can really do about that. So.
You might want to fix your collar.
What about my collar? My jacket, yeah. Because I don't wear jackets normally when I talk, but because of the stripes and the video, I have to do that. So. All right, so hope it's gonna not impede me to talk properly. And anyway, you will find other mistakes than my jacket. Okay, so, it doesn't work? Yeah, double click, okay. So just putting some background information first before we jump into the information. Just to remind everybody of some facts about oxygen. So the first thing is that, okay, we are always talking about the risk of oxidation and all the stuff, but we have to keep in mind that when we put oxygen in the wine, we do it on purpose almost, because it's not that easy to dissolve oxygen in wine. So we need to understand that, okay? We can avoid mixing oxygen with wine if we want. It's not going in wine like crazy, okay? You have some physical barriers there. The other important aspect is temperature. Okay, we know that temperature, low temperature, will favor O2 dissolution. So we need to be very careful about the temperature we're going to handle the wines because it will have an impact on the dissolved oxygen to start with. And then, of course, I think that we discussed that many times already today, but the matrix will affect the reactions, but also the dissolution. If we talk about wine or must, because of the saturation with sugar, you cannot dissolve the same amount of oxygen. So, and if you think about spirits, that will be another story too. So we have to keep this in mind. We don't start from the same point, okay? So then, if we look at this, we can distinguish two situations. The first one is what I call dynamic, where in fact, during pumping, filtering, bottling, okay, every time that you are going to move the wine, you are going to be in a situation where you get the kinetics of dissolution that are higher than the kinetics of consumptions that we talked before, okay? So you are creating a certain condition there. If you go to static conditions, here the kinetics of consumption will be higher than the dissolution rate, okay? Based on that, you are not exposed to the same risks and you are not going to do the same chemistry. So very distinct situations. If we think about oxygen pickup, I think, Maurizio, you said that, okay, I can pick oxygen almost everywhere. So it has still to be a dynamic process. Otherwise, it will be very difficult to dissolve oxygen. And you can play with the temperature and the exchange surface to increase the amount if you want to increase or to reduce. So typically, racking, cold stabilization, centrifugation, bottling, filtration, pumping, okay. These are all the steps where you can build some oxygen in your wine. The important thing is that at the end of the day, it's not just pickup that you can measure at one step. What is really important is the cumulated amounts of oxygen that you are going to dissolve. So here I just put some of the amounts of oxygen that we can measure when we measure in a finished wine that is in a tank, and then you go for cold stabilization, so you're going to pick 2 ppm. You go to filtration, 0.5, and then transfer another 0.5, and then you go to bottling, and then you can go up to 3 ppm. So at the end of the day, you are not looking at this step. It's 6 ppm of oxygen in total. And this is going to make an impact on the wine evolution. Okay? So now, what I want to do is to show you how we could measure all this. And today we have discussed many times about the NomaSense technology. So this technology is based on an optical technique, okay, that we are emitting blue light. Can you see it? Yeah? You see the blue light? Yeah? Okay. So I can move now? Breathe again? Okay, go. Okay, so this technology, okay, is based on emitting this blue light. We have sensors, so I'm going to show you the sensors. Very small, be careful. Okay. So they are protected in these black bags, okay? So we have this, like this. Can you see them? Yeah? Okay, so these little sensors, we can glue them in a transparent thing, like in a bottle, for instance, okay? And we are going to emit the sensor with the blue light, and then the sensor will get excited by the blue light, and then, depending on the amount of oxygen that you get, you're going to get a red light that will be emitted back to the device, and the time that the red light will take to go back to the device will be proportional to the amount of oxygen that is around the sensor, okay? So that's very basic physical principle, but that's the way it works, okay? So I'm going to show you some other accessories that we can work with. So I said that, okay, the sensor can be detached from the machine, but you can also, instead of the optical fiber, you can also use this probe, okay? In fact, I'm going to do that, okay? So can you see the tip of the probe here? Okay, in fact, here you have the sensor that is already included in what I would call a dipping probe or immersion probe. So this is the way that we can measure in tanks, okay? Just immersing the probe in a tank and get dissolved oxygen in a tank, okay? So I think that now I'm going to show you how we can do that, measuring bottles. So Maurizio, don't you mind? Okay, so in these bottles, maybe you can zoom on this. Can you zoom on the bottles first? Can you see the little dot in the headspace and the little dot in the middle of the bottle? You can see it? Okay, so the one in the headspace is to measure oxygen in the headspace. And the one in the bottle is to measure dissolved oxygen. Okay, so now you take it. Okay, so first maybe you look at me, what I'm doing, and then you look at him. Okay? Even that will be a shock to go from bad. Okay.
Sorry about that.
Yeah, okay.
It's hard life.
Okay, so I haven't, where are we? Okay, here I set the system to measure in hectopascal, okay? So if I measure oxygen in the headspace, I'm going to use this specific unit that is hectopascal, okay, to measure partial pressure of oxygen in a gas. So what I'm going to do is just hopefully I don't put my fingers too much in the, so you should see the blue light, okay, going to the sensor, okay? So that's the way I'm reading, right? The blue light is going through the glass, and I've got an answer back. So now if you can go to the screen, I don't know if you see the screen, you have a reading here. So it's 250. But okay, hectopascal in air should be 200, right? 200, 210. So what's going on here? Why do we have this 250 in the? It's because it was bottled just this morning for the exercise of it. And when we insert the closure inside, we are creating an overpressure in the headspace, so we are increasing the oxygen. Okay, so all of this is taken into account by the fact that we are measuring partial pressure. So we are very accurate in terms of the pressure that we can measure. Okay, so for the sake of it, for people that are interested later on, you can come and we can measure dissolved oxygen and headspace oxygen. We have 4 different bottles here. In fact, they are twins. Okay, so 2 are different from the others. We have made the dissolved oxygen varying and the headspace varying. So anybody can come later on and do a demonstration. But just because we don't want to use too much time on this, I'm gonna thank you.
Can I go?
Yeah, okay. Thank you. That was my pleasure. All right, so now we're going to look at the next slides. So just to show you that we can also have dots inside glass or inside glass that we can mount on tanks or on a, let's say, on a feeder tank, for instance. That's something that we can do. Okay, this is what I demonstrated. And just because I'm pleased to say that to you, we are going to launch the second generation of our NomaSense. So that will be for second half of the year. And in fact, here today, when we measure dissolve and then Headspace, we need to change units, and then we need to calculate back with an Excel file, if you will, to have the total amount of oxygen in the bottle. With this new version, that will be automatically integrated in the device already. So I call this a TPO meter. So we will be able to just clicking, measuring, and having the TPO information right away on the device. It will be lighter. Today it's a little bit heavy to carry on when you have to do an audit in your cellar. So that will be lighter. You see, I put my hands here, so it's very small. Even if I've got big hands, but I think it's still okay. Much more user-friendly in terms of the interface to navigate inside all the instructions that you get from the device. It's very easy. And also very important, there is a new sensor management, and that will be achieved through barcode. So all the sensors will come with a barcode. And then just by reading that, you will have the calibration information directly into the device. So you can run different experiments at the same time, different audits at the same time. You're going to store everything in a file structure, and you're going to be able to monitor over time the different evolutions of the different things. So that would be really a breakthrough in terms of the way this new device will operate. Okay, so now that we can measure in different places and different conditions, I think it is important for us to put some strategy in place about what are we going to do. Measuring, okay, that's good, but what do we do about that? So I used this slide from Nomacorc. That's a French company working on different topics around inerting, especially in France. And in fact, you can see that every time that you have a plus here, you can measure oxygen, and it can make some sense for you to know how much oxygen you are picking up there. And then from there, you can really try to start getting some sort of where are the critical steps where I should focus a little bit more time or make more efforts about preserving the wine. Okay, so what I try to do is try to look at the process in a much more, let's say, concise way. And in fact, we can gather in 4 different buckets. The first one is linked to fermentation, let's say. The other bucket is around maturation, aging. This one is more about wine conditioning, and here it's post-bottling. And if you think about the influence of oxygen in these different steps, you can really think that the 2 first ones you need to control, because it's probably not no oxygen that is good, but could be a little bit of oxygen that can, and of course here, aging, you need to know that you're going to play with oxygen, no problem. Post-bottling, we already said that we can control through the OTR of the closures. And maybe there is one step that you really want to avoid, is that when your wine is finished and you want to go into the bottle. I haven't seen any information yet, any technical information and technical data showing that it's good to add oxygen at that time. So here we should avoid, okay? So today, I would say that it's based on know-how and people experience how to handle the different steps. More and more people are using, NomaSense, but other technologies as well in terms of oxygen measurement. And we probably need to develop other technologies. We cannot stop here. We need to have other things. We talked about these SO2 methods that are probably reaching the limit of what we can do now. Now that we can better measure oxygen, we go to the limit of the analytical errors of a free SO2 method. So we need to develop other things, okay, along the way. Okay, so if we look at the control procedures, I took some examples here of stuff that we did, that we measured, and where we could interpret and use it in a winery to make a decision. So for instance, at the fermentation level, so here there was a must, okay? So you look at the must going from the press. So what we did is that we use a side glass here with a dot inside, and we could measure along the process for a system that was supposed to inert the must. So in fact, different cycles of the press, and every time it was inerted in red was much lower than no inerted here. So here, really, we could assess the process performance, that it was working like the manufacturer said it's going to work. But in some wineries as well, we use the NomaSense technology to really select the equipment that we wanted to buy, okay, with the wineries. So that's really a selection of the equipment. If we go to aging, here we did this very nice experiment on micro-oxygenation with Consorzio Toscania. He's now changed his name, but it's still renowned as Consorzio Toscania, where we had 24 different tanks there, and we ran different micro-oxygenation, and we were monitoring the evolution of dissolved oxygen in these tanks with Nomacorc. So you see here, I don't know if you can read, by the way, but very low amount of oxygen throughout micro-oxygenation, which is a very good indicator, okay? You don't want to have dissolved oxygen increasing in your wine. When you do micro-ox, you really want to have the oxygen that is added to be consumed and to be integrated in your tannin, anthocyanin kind of thing, okay? So that was really cool. But as well, we could use the system as an alert system, because some days we had the dissolved oxygen that was ramping up, and then we could stop before having to taste the wine and taste the acetaldehyde based on too much oxygen in the wine, okay? So it's like, okay, let's be proactive and react before the damage is done. Okay, another control, okay, I'm gonna skip avoid for the moment. We go to post-bottling. I think that we have covered already closure consistency from Malcolm's talk, and the closure oxygen ingress from different experiments already, Maurizio, but also Andrew and Jim. But just to, like you said, okay, from reduction to oxidation, these are the defects that we want to avoid. If we can play with oxygen ingress in the bottles, we can impact the aromatic compounds, so the aromatic profile, and we're going to impact color. And I still haven't found a nice picture of impacting mouthfeel, so if you have any idea, but it's there, right? You have seen that before. So really, we can really make wine evolution beyond bottling still under control, and that's very important. So I think here we have an interesting thing. We play with the different. So that's another way to look at the results that we have talked about already. That if we deliver different amounts, so you see this amount, the blue line, you create one aromatic profile. If you go to the red, you develop another, and then you go to green, and then you change dramatically by diminishing the reduction. And if you go a little bit more, you are developing more red fruit. So this is really the beauty, like Maurizio said, to have very nicely characterized oxygen ingress and, okay, being consistent to avoid the variation there. So we can really do a nice job in terms of wine evolution post-bottling. Okay, so that's for the control procedures, okay? If you want to think about avoiding, what can we do here? So we are going to focus on bottling, okay? And I'm gonna dig into that a little bit. So what we want to have in the control is dissolved oxygen, headspace oxygen, total package oxygen, which is the sum of it, and then total consumed oxygen, that Andrew talked about, is coming from the fact that we're going to have this plus the oxygen ingress from the closure, okay? So this is where you have the message in the bottle, in a way, in terms of oxygen going in. So, starting from audit results. So here, these are audits that we did in different wineries, different bottling lines, different closure technology, whatever. And here I put, okay, the green, like we are doing a decent job, and the red, we should maybe think about doing differently. And you see that you can find in the industry, and it's global, it's not the US, but globally in the industry, you can find a lot of differences, right? You have guys that are working like these, and some that are working like this, so there's a lot to be done, okay? So we are going to focus on two things. First, we are going to try to reduce the blue part, okay? How can we reduce dissolved oxygen in the bottle? And then we are going to look at how can we reduce the oxygen in the headspace. So in terms of reducing oxygen in the bottle, first of all, we could reduce oxygen that is already in the wine before being bottled. So if you are in a small winery and you get your tank of wine untouched for some months, okay, dissolved oxygen is very low. But if you just receive bulk wine, let's say a week before, and it was a lot of transfer and stuff like this, you can start from quite high level of DO. Okay, so then you can use some deoxygenation system to try to reduce that very rapidly. So we tested very different systems, and again, by measuring with the NomaSense, what we wanted to look at was the DO decrease, so going from 6 to, let's say, less than 1, but also the amount of nitrogen that you need to reach this level. Because if you are now going to spend a fortune on sparging with nitrogen and without getting a very nice improvements, maybe you should forget about that, right? So that's another way to validate equipments and to validate procedures in terms of the oxygenation. Okay, now we go into the bottles, okay? And when we do audits, what we try to do is that we try to take bottles at the beginning of the process, then during the process, and then at the end of the process. And very typically, curve that we obtain is this kind of U curve that, okay, this is true for bottling process, but it's true for filtering, for pumping. It's always like this, okay? You start with more oxygen, then you stabilize, and then you get more oxygen again. Okay, so let's try to see how we can influence that and what are probably the reasons why we get oxygen at the beginning. So this is typical thing that could happen, okay? You start with your wine in a tank, you want to bottle, and you have this line, and then a pump, and then a filter, and then something here, okay? But it's full of air. So the first bottles will be very much impacted by wine mixed with air, so oxygen, and you have the first bottles that are very much impacted. Okay, so what we can do to reduce that is to first inert the line, and then start going into the bottling process. Okay? Now, we are observing this, okay? So that's quite flat. Okay, here we are, let's say, 0.7 ppm, which is okay, right? We go there, so the system is running, so you have evacuated all the air that was pocketed in some of the pump area or the filter or whatever, so you are in a nice process, so you don't really mix with air, so it's okay. But okay, maybe we can do a little bit better, is that instead of letting the tank with air on top of it, you start inerting the top of the tank, and so you are doing a better job here. So that's a way to reduce your 0.7. Maybe you can go to 0.5. Okay? And some other thing that you can do is that you can inert the bottle before filling. So depending on the bottling line, on the bottling facility that you get, you can inert already the bottle before. So we have done a lot of tests there, and generally speaking, we can reduce dissolved oxygen by 0.5. That's almost the maximum that we can reach. So that's good, that's an improvement. Okay, we need to think about if it's the most important thing that we should do on the bottling line, okay? And now I go back to the bottles at the end of the process. And here what's gonna happen is that, in fact, I'm running with very low level of oxygen. It's probably not perfect representation here, but I have very low level of wine, and I need to push my wine into the bottle. Okay, so here I'm gonna push with air, or I'm gonna push with water. But I could also push with nitrogen and do like a flush of nitrogen to push the wine going into the bottle. So that would be a way, if we could implement all the green stuff that I presented before, to have from the first bottle to the end of the line, the same thing in the bottle. So we were talking about variation, inconsistency coming from the closures. You have also a lot of inconsistency coming from the bottling line itself. But we have tools today to do stuff that could make sense, right? To have much more consistent process. So that was about dissolved oxygen. So let's have a quick look at Headspace oxygen. So here we did an experiment in Germany, Riesling wine, same dissolved oxygen in all the bottles, but what we made varied was the amount of oxygen. Okay, you see 0.4, 2.9, 5.7 in the Headspace, by changing the way that we were inerting the bottles. And in fact, what you see here is that you have a nice impact, like it's almost 15 ppm difference between the one that is well managed and the one that is out of control. So the oxygen from the Headspace has a very strong impact on free SO2 drop, okay? So I know it's cool to talk about dissolved oxygen, but please don't forget Headspace. Because 2/3 of the oxygen, if I take 300 audits that we have been carried out, 2/3 of the oxygen is generally in the small Headspace and not in the wine, okay? Because like I said before, it's easier to have oxygen in the gas phase. It's a challenge to have oxygen dissolved in a wine. So we know that this is what we want to measure in the wine, but be careful, what is on top of the wine can be much more risky than what's inside, okay? And this is the kind of thing that we could achieve. So these are, okay, results of audits and different things like this. So here I'm talking about inner seals, okay? So you still have places where people are bottling with no vacuum at all. So here, generally speaking, we are talking about 3 ppm in the headspace, okay, or more. Then if you apply vacuum, I think you know, but don't think that vacuum means zero oxygen, right? It's a partial vacuum. So best case, you reduce by half. So when you start high, you're still very high, okay, 1.4 here. Now if you start doing sort of a mix between vacuum and CO2 or nitrogen, we personally prefer CO2 in the case of inner seals, because CO2 will dissolve right away. You don't have an overpressure in the bottle, so it's, in our opinion, much better. And you can go as low as 0.2 ppm, which is nothing, okay? So here you save. You're doing a very nice job, okay? That's inner seals. If we go to screw caps, the situation is, I would say, almost the same, that if you don't inert, you get 3 as a minimum, and you can go much more because you get a bigger volume of headspace, okay? Because you don't have the volume of the closure inside the bottleneck. The systems that are currently in use for inerting headspace are working so-so. And that's interesting to measure sometimes and to compare with what the manufacturers would say it would bring. You need to be very critical and measure. Okay, so you can go to a situation where you are doing vacuum in under inner seals, okay? And what we are doing at the moment is that we are testing new methodologies, new methods to inert in a different way bottlenecks. And with this method, we can go down to 0.6, 0.5 ppm of oxygen in the headspace. And that's quite promising, because that can work nicely even if the line of if the speed of the line is quite high. Okay? And the other thing that we are working on now is to try to manage TPO at once, so DO and headspace at the same time. So we are testing different technologies like this one. So in fact, here what you are doing, so here you get a bottle, okay? You're gonna have the head going at the bottom of the bottle. So you are filling from the bottom. So first thing that you are doing, you are creating less turbulences. So that's one way to avoid the dynamic process. So you are reducing already dissolution. If at the same time you are flushing nitrogen, or just before filling you are flushing nitrogen, nitrogen will sort of blanket the wine while you are filling it, okay? So you keep a blanket of nitrogen on top of it. So we have checked that this is working very nicely. So dissolved oxygen here can be very, very minimal in terms of pickup. And what we think it could do is that if the blanket is good enough, we can keep the nitrogen blanketing effect in the bottleneck. And before closing, we would have sort of, if you are now take a vacuum system on something that is enriched with nitrogen, the vacuum effect would be even better in terms of reducing oxygen. So, but to be checked, and that's something that we need to do next week or the week after next. Okay, so we have ways of diminishing headspace oxygen. So if we think about the conclusion of what I was saying today, okay, we have lots of possible variation during wine conditioning, wine bottling, okay, but we have already some solutions that we could put in place. But it starts with first measuring and continuously measuring, okay? It's not because you are measuring one day that you save. You will have something that will be drifting from the setup that you have, because you you have some problems at one filling head, one corking head, somewhere. So it's good to measure. Okay, like I said, the technical solutions exist. Okay, we need to monitor and evaluate the system that we put in place. So I like this. As an industry, we can do better. When we have seen the first draft, the first slide from Malcolm about the SO2 variation in wines that are in the market today, I think that we have to do better. Okay, and now I'm going to try to just put a sort of a general conclusion from everything that was said today. So I'm using this slide. So try to follow me. Okay, so when we think about a bottle of wine, we said that we have the first source of oxygen is dissolved oxygen. That can come from what was done in the winery before, but can come also from the bottling process. Then we are adding oxygen in the headspace. And we have another source, which is oxygen ingress through the closure. Okay? From there, we can measure the TCO, right? Okay, so first thing is that the TPO, so these two guys together, if it's not controlled, that can mask the OTR effect. So that was one of the comments of Malcolm at the beginning. He said the first time that we looked at the results from the different permeability trials that we did was some sort of messy. Why? Because we never measure how much oxygen went in the bottle before closing it. So it was all over the place, but it was coming from bottling. It was not coming from the lack of performance of the closures. Second thing is that we said that, okay, now we have oxygen going into the wine, and that oxygen will get consumed. It will not stay here. It will react with the wine, okay? So it's going to get consumed. And we introduce this very important concept of the total consumed oxygen, and that's really something new that we are bringing now to the table and into consideration in terms of, okay, what's going on in a bottle. If we take one marker, and I know it's not probably not the best one, but at least everybody understands this marker about free SO2, okay? We have seen that if wine is consuming oxygen, we're going to see some loss of free SO2, okay? And between this TCO and the free SO2 drop, Andrew did a nice presentation about the fact that we can now start finding some correlation there and trying to think about what are the wines that are at risk or not. Okay? So after a while, because it's consumed, your dissolved oxygen disappears. You go to very close to zero. Headspace had been transferred, dissolved into the wine and reacted, so it disappears. So what gets the most important factor is the permeability of your closure, making the wine developing over time. Okay? So, okay. Some situation, like Andrew mentioned, is that sometimes because the wine cannot cope with this oxygen anymore, you can have a little bit more of oxygen, dissolved oxygen, or oxidation going very deep, I would say, to a point that you are really losing your protective factor. So you don't have preservation factor anymore. You are losing your free SO2. So you are going under this 10 ppm of free SO2 that is accepted to be the limit that you don't want to go below. Okay? Other situation, okay, and this leads to oxidation. Yeah, sorry. Okay. Other situation where you don't have enough oxygen, in fact. And so you stop almost the oxidation things, but we have seen that if we stop oxidizing the wine, you stop your color evolution. But also you go to the other chemistry that it's happening about the sulfur compound. So you are creating other molecules or expressing other molecules there. So you can be happy because you keep a little bit more of free SO2, so you are preserving the wine shelf life in a sense. But as a result, you can develop another problem that is reduction. Okay? And just to conclude about that, Malcolm showed us that consumers care. So we have to be very careful and prevent oxidation and reduction defects that we have seen is still 50% of the defects that could be shown during an international wine challenge competition and tasting. So this is where we can really do a better job by pleasing our end consumers. And that's about it. Thank you very much for your attention.